Welcome to the educational module Introduction to the Internet of Things of SendingVet program. The current section is to introduce you to the architectural design and applications in Internet of Things. IoT applications can be described as things or devices, sending data or events that are used to generate insights, which are used to generate actions to help improve a business or process. An example is an engine, which is the thing, sending pressure and temperature data that is used to evaluate whether the engine is performing as expected. This insight is used to proactively prioritize the action, which is the maintenance schedule for the engine. This diagram provides a high-level view of the IoT architecture. On the left-hand side, we observe the physical entities which are located at the edge of the network. These entities are equipped with technology so to measure their state or collect data from their immediate environment. These data are called telemetry data. Edge devices are connected to the server-side infrastructure over a variety of methods, including cellular networks, Wi-Fi, Bluetooth, and so on. The connection to the server-side infrastructure can be direct or through an IoT edge gateway. The server-side infrastructure provides tools and services to gather, process, store, and analyze data collected from edge devices. In addition, quite often the server-side infrastructure provides configurable and highly customizable widgets and dashboards that visualize data. Data visualization is merely used for monitoring of edge devices and their immediate environment. Data visualization helps people understand patterns, trends, and insights by transforming data into a visual context. IoT edge devices are the key ingredients in the overall IoT system. Edge devices are physical entities with sensing and actuation components. Sensing components monitor the state or the parameters of an edge device and its close environment. Actuation components can change the state or the parameters of an edge device. Beyond sensors and actuators, an IoT edge device needs to incorporate processing, storage, and communication capabilities. The reason is that data generated from sensors need to be either locally processed and stored or sent to a more capable server-side infrastructure for further processing and decision-making. Also, remote device management functionalities for configuration and control, monitoring and diagnostics, and software updates and maintenance require communication with the server-side infrastructure. IoT edge gateways have emerged as architectural components that improve the performance of IoT networks. The IoT edge gateway is a physical device or software program that lays between edge devices and the server-side infrastructure, usually closer to edge devices, aiming to bridge legacy and next-gen devices to the Internet of Things. Gateways can provide device connectivity to edge devices lacking Internet connection capabilities, protocol translation to edge devices that do not support IoT-related protocols, data storage management and edge analytics to high-end IoT systems requiring fast decision-making, as well as secure data flow between edge devices and the server-side infrastructure. The server-side infrastructure consists of hardware and software components such as physical servers or virtual servers, operating systems, specific software, and cloud-based services that are needed to support the computing requirements of an IoT system. The server-side infrastructure is usually provisioned with a vast range of capabilities, from storage, networking, and processing power to data pre-processing, natural language processing, artificial intelligence and machine learning algorithm. The server-side infrastructure is responsible for collecting, storing, processing, and analyzing data collected from edge devices, perform intelligent decision-making based on collected data, and send actionable commands and notifications to edge devices. There are several technology options for implementing the server-side infrastructure which will be analyzed later. Edge devices can generate continuous stream of data, where the time interval between successive data updates is very small, usually minutes, seconds, or even milliseconds. The massive amount of generated data is called big data. Quite often there is a need to process big data almost instantaneously for fast reaction to detected events. However, big data cannot be stored and processed on typical IoT edge devices and IoT gateways due to limited local resources. In traditional IoT application setups, data produced by edge devices is relayed back to the server-side infrastructure for further processing. Once that data is processed, further instructions are sent back to the devices out on the edge of the network. There are two problems with this setup. First, it takes time for data to travel from the edge device back to the server side for processing. This delay might only be a matter of milliseconds, but it can be critical, especially for mission-critical, real-time applications. Secondly, all that data traveling back and forth between the edge and the server side of the network puts tremendous strain on bandwidth. Another problem that emerges in server-side computing is that data become available to infrastructure providers. This poses important privacy considerations since over the last few years new regulations dictate that data cannot leave the country. Fog and edge computing in IoT applications are network and system architectures that attempt to collect, store, analyze, and process data originating from edge devices more efficiently than the server-side infrastructure. In other words, both fog computing and edge computing involve pushing intelligence and processing capabilities down closer to where the data originates at the network edge. These architectures share similar objectives, namely, to reduce the amount of data sent to the server-side infrastructure, to tackle connectivity bottlenecks thus leading to decrease of network congestion and end-to-end latency, to improve security and privacy of data and to improve system response time in remote mission-critical applications. There are multiple technology options for deploying a server-side infrastructure. The first option is obtaining a physical server. A physical server is a single-tenant computer server, meaning that a specific physical server is designated to a single user. Each physical server includes memory, processor, network connection, hard drive, and an operating system for running programs and applications of the single user. Another option for deploying a server-side infrastructure is obtaining a virtual server, also known as virtual machine. A virtual machine is a software computer used as emulation of an actual physical computer. A virtual machine operates in a multi-tenant environment, meaning that multiple virtual machines run on the same physical machine. In this case, the computing resources of a physical server are virtualized and shared among all virtual machines running on it. Another option are containers. A container is a standard unit of software that packages up code and all its dependencies so the application runs quickly and reliably from one computing environment to another. A container can run on top of physical server or a virtual machine. Another option for deploying a server-side infrastructure is the cloud. Cloud computing is the provision of shared resources as for example, hardware, data, and applications as a service over a public or a private network. More specifically, cloud computing provides as a service the products of virtualization, on demand, either to the users of a public network i.e. the Internet, or to the users of a private network owned by a company. Customers are adopting cloud-based infrastructures because of the rich data-oriented services such as data ingestion, data transformation, advanced data storage, data processing, data analysis using machine learning, and artificial intelligence algorithms and integration with a large variety third-party databases. The IoT is becoming more and more used in several areas of activity since it enables the creation of a myriad of applications and services. Some of the IoT application domains are smart city, industry, and health and welfare. The smart city domain comprises IoT-based services applied to different areas of urban settings. Smart city applications envisage the best use of public resources, improvement of the quality of services provided to people, and reduction of operating costs of public administration, establishment and improvement of services focused on mobility and intelligent tourism, providing, for example, information about the state of roads, occupation of parking lots and the history of tourist attractions. Smart grids allow for better management of the network through new information on energy consumption. Intelligent building allows new forms of residential automation, and infrastructures for monitoring and controlling. Finally, public safety and environmental monitoring, facilitating the management of environmental disasters and strengthening the security of buildings open to the public. IoT-based services are also used in the industry domain, such as in agricultural activities, factories, and issues of logistics of resources and products. In agriculture, IoT applications are used to perform the monitoring of soil moisture and the conditions of the plants, control microclimate conditions and monitor weather conditions that can damage the crops. In the factories, we can find applications for monitoring of pollutant gases, locating employees, and improving the manufacturing process. Moreover, in logistics issues, IoT-based services can be applied to the improvement of the processes involved in supply chains. In the domain of health and wellness, we find IoT applications used for monitoring and diagnosing of patients, and for managing of people and medical resources. IoT-based services applied to the health domain enable the creation of applications to remotely and continuously monitor the vital signs of patients in order to improve medical care as well as enable the identification and tracking of equipment in a medical institution. When designing an IoT system, there are several functional and non-functional requirements that need to be fulfilled. The functional requirements relate to the actual functionality that the system to be developed needs to have, while the non-functional requirements, also known as quality attributes, relate to the quality of the system. While functionality is provided by the implementation of the system, the quality attributes are introduced in large part by the software architecture. Therefore, the goal of software architecture is to design a system that meets the requirements set for certain quality attributes. Choosing one software architectural style over another will exhibit different levels of quality attributes for the same system. In this presentation we will not get into further details related to quality attributes. Nevertheless, in the specific module of this IoT course related to architectural design, we show why the aforementioned quality attributes can be important in the Internet of Things. IoT systems are designed and developed on the basis of software architectural styles. A software architectural style is a general, reusable solution to a commonly occurring problem in software architecture. The choice of which architectural style to use, based on a given set of quality requirements which should be specified by system architect, should be the first step in software design. In this course we will focus on the following styles: client-server, peer-to-peer, pipes and filters, event-based, publish-subscribe, service-oriented, REST, layered and microkernel, which will be described in detail in the specific module.